Okay, now that we've talked about inscribed angles and what they are, it'd be great to know how to figure out their measure and how they relate to the circle that they are inscribed in. And you can see what I've done over here on the very far right is to create an inscribed angle. Angle C is inscribed in a circle. And the proof, it's important to say that we have three situations. The inscribed angle could contain the center, like it does right there. It could, the center could fall right on one of the chords, and in which case CD is a diameter, or the center could be outside, and we would want to know all three of those situations. So the quick proof over here is really actually pretty neat. And if you look at the first option where the center is on the angle. So we've got the center up here, and if I draw in the central, let's say this is x degrees out here, right? Well, if I draw in the central angle, we know that this is also x degrees inside. Whoops, can't really get that to happen. Okay, so x degrees inside. And you'll remember back from when we dealt with triangles, that if I had, and this is really important for these proofs, if I have a triangle, any kind of triangle, and I have an exterior angle, you may remember that this angle on the outside turned out to be the sum of these two on the inside. And so back to this proving the inscribed angle theorem, if this is x degrees over here, right, we know that these two have to add up to x degrees as well. And what's so awesome is that this is an isosceles triangle on the inside of the circle. So these are both radii. And so this is an isosceles triangle, and what's nice is that you can see pretty quickly that if this is x degrees, let's say it's 20 degrees, each of these has to be x over 2 or 10. Right? So the measure in that case, right, it's pretty clear, the measure of the inscribed angle is half the intercepted arc. Half the intercepted arc. This is the theorem I'm proving over here. Measure of angle ABCD is half the measure of the intercepted arc BD. Let's take a look at the situation right here, which is the second one. What happens if the center is on the interior of the inscribed angle? Well, not too bad. The proof goes something like this. Create exactly the first situation. Put one right here, right? Because we know that if this is x degrees, we just proved that this angle over here is x over 2. Well, what happens if that's y degrees? What if this little piece is y degrees? Well, that's, right, that's y over 2 by the same principle as what happened up here, right? And so when you look at these and you add them both together, of course, x over 2 plus y over 2 is equal to x plus y over 2, and we've made the proof the same thing, that this whole arc, right, sorry, this whole angle, this inscribed angle, is half the intercepted arc. All right, and finally down at the bottom, what happens if the center is on the exterior, right? Do we still get back to x degrees? And in the second case, we used the addition property. Down here, we're going to use subtraction. I'm going to still draw in the situation that we already proved. This is what happens in math quite a bit. Start with the first situation and then apply it multiple times. If I have this as, let's say, x degrees, right, and this whole thing, right, is k degrees. Well, I know from situation 1 that this whole thing right here is k over 2 degrees. And I know that this piece right here, the small one, let's say this, is y degrees. So y over 2 would be the small angle. And if I'm looking for this piece right here, this piece on the inside, right, I would say, of course, that I would want to subtract k degrees from y. So we end up with k minus y over 2. But k minus y turns out to be what? It's just x, according to the picture and according to how I've set this whole thing up. Okay, so again, we've proven it all. And here's the proof of the theorem all the way through. Let me just see if I can clean up some of this stuff. I certainly don't need this, don't need this, don't need this. Okay, a few things at the bottom that are important for me to point out. A corollary is something that kind of flows from a theorem. So down here we have 3 corollaries. One of them is pretty straightforward. If, whoops, God, I didn't mean to do that. Well, let's see, let's go back here. The angle inscribing a semicircle is going to be 90 degrees. Well, again, you can imagine that if you have a circle, let's see, circle, right? And let's say you've got an angle that is inscribing 180 degrees, right? This angle has to be half of 180. Similarly, what did I do? I moved that around. Whoops, this one I meant, that one flew around. Angles that inscribed congruent or the same arc are congruent, right? So if I do, let's get rid of this. Let's say I've got a circle. Let's do a nice one. Circle with center radius right here, create a radius of 2. Okay, and what happens if I draw in, let's say, here's arc, and I draw in this here, but then I also look at this one, right? You can make the argument, of course, that if this is x degrees, each of these is x over 2. So therefore, they are congruent. So what we say is that angles that inscribe congruent or the same arcs are congruent. All right. And finally, opposite angles of a quadrilateral inscribed in a circle are supplementary. This one is kind of funny, but you can also imagine that if we have up here, right, if I'm looking at this inscribed angle, right, which covers, let's see if I can change the color here quickly. This is going to inscribe this whole arc. And let's say that we have purple, right? They are opposite sides of a quadrilateral. That's going to involve here. Well, you know that purple plus red has to be 360. So each of these, if you add them up, must add up to 180, right? And supplementary is 180, so they add up to 180. Okay, so a separate corollary that's related to the fact that the main theorem here, which is huge, right? An inscribed angle is half the intercepted arc.